Hello, everybody. My name is Steve Miller, better known as Kelly's dad and marketing gunslinger, and I am here to welcome you to the MTConnect Student Challenge webinar series. This is webinar number 1. And first of all, I want to make sure you understand something. That is that I know nothing about this, okay? I am not an engineer. I'm just the guy moderating this. I have 3 very, very smart, I'm going to say very, very, very smart people, since it's 3 people, 3 varies, right below me down here, who know everything there is to know about the MTConnect Student Challenge and anything to do with MTConnect, and they're going to be talking about this here in just a couple of minutes. Let me introduce them to you. We got right there in the middle, okay, she's kind of sandwiched in between. There is Helena Hailu. Did I pronounce your name correct, Helena?
Perfect.
Thank you very much. You know, and Helena is the MTConnect product manager for the MTConnect Institute, which is part of the Association for Manufacturing Technology. And then right below her is Mr. Tim Shinbura, who is the Vice President of Manufacturing Technology. And I have to say this is important. This is an important title. Because
it's only important in travel, though. That's
well, when you consider the fact that the association's name is the Association for Manufacturing Technology, and you are the Vice President, you know, of Manufacturing Technology, wow, that makes you, you know, we got the bigwigs going here today. And you talking about bigwigs, we got a serious bigwig here with Mr. Will. I'm sorry, I put Will in there. Sorry, Will. Will Sobel, I should say, right? Is that correctly pronounced, Sobel?
Yeah.
Yeah.
Either way.
Either way, okay.
I'll answer.
All right.
And Will is fine.
Will, okay, good. You know, I know we call you Will, but I didn't want to, you know. Anyway, so and Will is Chief Strategy Officer for System Insights Incorporated, and Will is the star of the show, of the video that you're about to see here, you know, in a few minutes. But first. We want to learn more about the Student Challenge. Now, in these webinars, I need to make sure that you understand that while we're doing these webinars, that these sessions are being recorded. And for those of you that are live, you can submit your questions anytime in that little Q&A box down below. When you submit them, we will see the questions. Nobody else will see the questions, so don't be afraid to ask something that you might be embarrassed about. Don't know why you would, but okay, just go ahead and submit your questions anytime. We will follow. We'll track those. Also, and you know, get your pen out. You know, on Facebook, if you go to the Facebook link here, and we will provide this later on. We will find somewhere where we can put this for you. That there is a page for the MTConnect Student Challenge, or is it MTConnect, Elena? What is that page?
The page is the MTConnect Institute's Facebook page, and on that Facebook page you'll find an event for the Ideation Student Challenge. Yeah,
and you'll be able to ask questions on there, and you know, get into discussions with other people as well. And then also, for those of you that are interested, we will have a second session next week on Tuesday, December 1st. Same time, same bat time, same bat channel. Of course, if you're watching this as a recording, then you won't. It'll be too late. So anyway, anyway, so now I want to turn it over to Elena. And Helena, you tell us about the Student Challenge. Okay, it's all yours.
Got it. Thank you, Steve. So the Student Challenge is sponsored by the Office of Secretary of Defense, Defense-Wide Manufacturing Science and Technology. This is the second competition, innovation competition, that is sponsored by OSD DMSNT. I'll tell you a little bit about the first one while I'm in the process of telling you about the one that we have right now. The very first Student Challenge was open to all of industry, and interesting enough, the first place winner was a student. This particular challenge, though, is open to only community college and university students, both at the undergrad and the graduate level. The competition has a total of $33,000 in cash prizes. And you'll see later that it's a good idea to use this opportunity to write about or submit some of the projects that you may already be working on, whether it's your thesis, an internship project, or a capstone project. So the Student Challenge is two distinct competitions. The first one is the ideation competition, and the second one is the application competition. The ideation competition requires that the students identify challenges in manufacturing, describe what potential solutions, and write a 5-page proposal. Now, the solution should use MTConnect data, and you'll learn a little bit about MTConnect data when Will does his session. There are 5 prizes associated with the ideation competition, and they range from $5,000 to $1,000. The application competition, we're asking students to identify, again, a challenge in manufacturing and develop software that uses MTConnect. The government does not want your source code, but what we do ask that you submit is a video, an abstract of the software, as well as an icon we can use when we publish your submission. There are 3 prizes associated with this competition, and they range from $10,000 to $5,000. The evaluation criteria for both the ideation and the application competition is essentially the same. We're looking for ideas and applications that benefit the manufacturing industry, that are creative and innovative, something that's not currently in the marketplace. Practical in concept, should be impactful on the industry. This is somewhat similar to benefit to manufacturing intelligence, where the 4th circle you see here is more about the industry, and the first is more about technology. And lastly, overall quality. Overall quality speaks to the quality of your submission. So did you read the rules and regulations? Did you submit a 5-page proposal opposed to 4 or more than 5? And did you submit a full package? That's what overall quality speaks to. Key dates and deadlines. The ideation submission period will end on December 15th, and the application submission period will end on January 31st of 2016. Note that the winners of the ideation competition, as well as the finalists from the application competition, will be invited to MC Squared, which is a digital manufacturing conference, in April of 2016. This is a great opportunity for those who are winners of the ideation, as well as finalists in the application competition, to come and engage with industry at this industry-focused conference. Earlier I mentioned that the top prize winner of the last MTConnect Challenge was a graduate student at the time. So who you see over on the left is Valerie Pizzulo. She's a graduate student. She was a student at Clemson. And over to the right is Joel Neidig. He submitted a solution that uses Google Glass and marries it with MTConnect such that you could look at a machine tool and look at data about what's going on with that machine tool at the time. Now what's interesting about these two is Valerie came to MC Squared last time and got a bunch of job leads. Joel Neidig also came to MC Squared, and post his winning, companies like GE were interested in his solution. So the MTConnect Student Challenge, these are the two websites where you can find the rules and regulations associated with each of the competitions. And it's a great opportunity for college students to network with industry and really to submit ideas and applications that could potentially revolutionize the manufacturing industry.
Thank you, Elena, very, very much. And I do have a question about the participation. So I assume that employees and people like me can't participate, right? We can't go for the bucks.
Unfortunately,
Yeah,
unless
unfortunately
you're
not.
a college student.
Yeah. Okay. Well, I'm going to get back to you with questions about this. All right. But thank you very much, Elena, for explaining this. Once again, we want to make sure that you know that you can contact. Let's see. I think I stuck another slide in there. There we go. I stuck another slide in there, so you can contact Elena with your questions, or you can go to that Facebook page that we talked about. So thank you again, Elena, and we will get back to you very soon.
So now that we've learned about what the MTConnect Student Challenge is all about, let's give you a little bit of background. Will Sobel, who I introduced you to already, has gone around the country, spoken at several different campuses, putting on seminars for students and faculty all over the U.S. about what MTConnect is. And it gives you a really, really good background so that you better understand how you can plan your projects and prepare your projects for submission. In addition to Will being the Chief Strategy Officer for System Insights, as I introduced him, he is in fact also the Chief Architect of the MTConnect Standard. So kind of makes him know what he's talking about. So let's join him now into part one of this MTConnect seminar.
I'm going to talk about the digital thread and about some background material. I also like to get some feedback from everybody about your background and whether you've had any experience in manufacturing, and sort of tailor some of the content to what you need to know to be able to participate in the challenge. So a little about me. I am the Chief Strategy Officer of System Insights. That's my company. We do process analytics, so we do big data analytics on manufacturing, for manufacturing. Primarily discrete manufacturing. I'm also the chief architect of MTConnect. So I've been working on this standard for 8 years, and I'm the one who actually writes a lot of the documentation and kind of puts together the structure and the protocol and everything else. So that's why I'm up here talking about it. And I'm also, has anybody heard of things like the Industrial Internet Consortium or Industrial Internet of Things and that kind of thing? Okay, IIC is, I'm also one of the chairs of IIC for analytics. So that's kind of my background. I'm from the financial industry, so I come out of developing large-scale financial systems for real-time risk management and trading systems and other fun things like that. So there's actually some similarities, but I'm not going to get into any of that. So back to it. So basically, the drivers for what we're talking about today, and why do we care about data? Why do we care about manufacturing? Is this. So if you look at the entire sort of field of Internet of Things, has everybody heard of the Internet of Things? A lot of it comes into consumer. So you hear a lot about things like Fitbit and various different devices, cameras you can put on your cat, all these kind of things. So that is one piece of it. But what often people don't realize, if you look at the way, this is actually a McKinsey report, and if you look at the breakdown of where the big money is, all along here, factories, manufacturing, operation optimization, predictive maintenance, industry optimization, $1.2 to $3.7 trillion of available value. So that's why we care. So we care because basically this is our biggest sector. If you look at all the other sectors, nothing even comes close to the size of manufacturing. They're all about half, even the biggest ones like health and so forth. So it's definitely something that we need to focus more on. And the problem is that a lot of the people who are in things like manufacturing engineering and some of the sciences don't cross over into some of the technologies, and that's where this is trying to encourage people to get the background in both areas to be able to apply some of the data and analytics to the manufacturing sector. So is everybody familiar with things like discrete manufacturing, differences between like process, continuous process and discrete?
I can guess yes.
Okay, so get into it a little bit. Discrete manufacturing is where you have single parts that are made, so it's not a flow of material, like we talk about pharmaceutical and food, where you have these continuous flow of material coming through, and energies, where you're processing, usually pumps and automated machines, very bespoke, versus discrete manufacturing, where often you're doing things like metal removal, or composite, or something along that line, where you're dealing with an individual part that's slowly being transformed through multiple different processes to a final shape. A lot of our high-value manufacturing, things like automotive and aerospace, are all discrete manufacturing. So it's definitely one of the highest value areas of manufacturing in general. And the standard that I'm going to talk about, MTConnect, is actually focused primarily on discrete manufacturing. So discrete is basically taking something like here you have a raw forging of a drive shaft, you do a series of machining steps on it, you come up with a finished part, and then there's an assembly process where you put the various bits and pieces together. MTConnect, again, to even narrow a little bit further, is interested in that manufacturing step, basically the processes that are involved in either additive or subtractive material. So basically adding or removing material from various pieces of metal, plastic, whatever. And the other thing that we're concerned about, and we're getting into right now in a big way, is process flow. So if you think about things like the digital thread and how manufacturing is executed, it's not just on one machine. Basically, you go from machine to machine. There's things like, this is actually the process for making a drive shaft. There's all these different processes, and each process is executed on a different set of machines. So there'll be travel time, part handling, setup and tear down of those different machines, and so forth. So we're concerned about basically all of these timings and how the process flows, how effective it is, and how optimally we're executing those different processes on those different machines. If we think about it from the standpoint of data, the machines on the floor are giving a huge amount of data out. So if you look at your standard like CNCs, lathes, and everything else, don't try to read it. I'll give you examples later, sorry. So you're getting a lot of data out of these different machine tools. But to be able to actually do some analytics and to be able to understand how the processes are performing, contextualized within the entire manufacturing process, it's not possible now because there's this barrier here between the information coming off of the machines and whatever kind of analytic applications you have. If we look at the entire market, we look at what's going on right now, 95% of the shops out there are what we consider dumb. Basically, data collection and even basic monitoring. Collecting data from machines, understanding what the machines are doing at any point in time is very low. Basically, the number of shops that are actually doing this, especially if you talk about the small to medium manufacturers, I'll get into those in a second, very few of them are actually doing anything even simple like monitoring. We have monitoring applications, a lot of those out there today. So this step here is not too hard to get to, but a lot of people are still using paper and pencil and stopwatches. The next step up is things like real-time analytics. That's when you take the data and you start analyzing the data and you start understanding what's happening, why is it happening. So you're able to take your basic monitoring, backward-looking reporting, and start to predict forward, like, okay, the machine is down, why is the machine down? Can we tell from the data and the context of the process why this machine is not operational right now? The next level you can go up to is proactive, where I can now say, I see that this machine is about to go down, let's do something about it. Let's alert somebody so it doesn't go down and we don't lose production. That's a proactive step. The next is predictive, where I can actually look at, okay, historically, when these sets of circumstances occurred, I can predict that this is what's going to happen in the future. So I can actually look at each one of the steps I can see how the processes are laid out and how the interleave is going to happen. And I can see that there's a tendency, if I do this set of steps in this order, something bad is going to happen right around there. And now you can get more predictive about your maintenance, about your quality, about your yield, tooling, etc. The next step is where the systems actually start to self-optimize. So we're still talking about human-in-the-loop processes. Now we start talking about things like self-optimization, where you can actually have the processes figure out optimal strategies for being able to manufacture parts. It's not just where I'm going to have a set of pre-described weekly schedules. Now the system can work around various different congestion, maintenance issues, tooling issues, process issues in near real time or real time, make decisions, even decide, send it out, keep it in, these kind of things. Of course, the final is, where we start getting into, your T2 Cyberdyne type scenario where, machines take over the world and, kill all the humans. But that's to come later. So we're still trying to get to this step here. We're a long way from that. So anybody familiar with the small to medium manufacturer? Has anybody worked in like a shop or done an internship there? Okay, so a few people. That's good. More than I had last time. So small to medium manufacturers are typically companies that are below 500 people and modest revenues, but they do make up a large portion of our industrial base. So if you look at number of firms, there's actually around 250,000 firms out there right now. So it's a huge number of these. This is in the US. This is actually a couple years ago, census data. So there's a large number of these. They employ nearly 5 million people. There's a huge number of also ancillary companies associated with it too. If you look at on a total small business, it's number 4 here, not too far behind. So this is like health and then retail, food services and so forth. And manufacturing is way up there. And actually in money, high value jobs, it's pretty high as well. That's one reason why the government is focusing on this so much, because there's actually a need to be able to build and maintain this base in the US. So we think about how they interoperate with everybody else. So basically we look at sort of a supply chain tiers. Your OEMs are here. Those are big companies like Boeing who sell aircraft. But if you look at Boeing or GM or any of these other big companies, there's actually a huge number of tier 1s and tier 2s and all the way out to like tier 3, 4, 5 suppliers that come in and provide parts to those companies. They don't make everything themselves. Actually, a lot of innovations come out of your smaller SME shops. And like Itamco is a good example of it. That's actually the guy who won last time, Joel Neidig, who did the Google Glass thing. He works for Itamco, very creative guy. And they are a big supplier to Caterpillar. They do a lot of the huge gears and parts that go into Caterpillar equipment. So, and they're, I think, around a tier 1 or tier 2 supplier as well. And then, of course, you have the other direction, which is the customers and the supply chain going out this way. So you look at aerospace and automotive, there's these very deep, complex supply chains, redundancies built in. If you ever looked at anything like from Apple and Tim Cook, they have this, mesh of companies that supply parts and components so that, that can never go down. There's another type of SME also. I'm going to use Task Force Tips, actually a customer of ours, who makes water cannons and nozzles and really cool firefighting equipment. And they're actually in Valparaiso, Illinois, and they are, this is another type, but produce very specialized parts, complex specialized parts, and they are the leader in this type of equipment in the world. So they're incredibly innovative, and they have fairly small production because there's only so many of these things that are needed out there, but they knock everybody else out. So there's these types of companies there. And this is, they deal with the complete product life cycle. So if we talk about supply chain SMEs, they're usually getting designs and requirements from other companies and then developing products for another company, versus these types of companies which are actually going from the initial ideation part where they think about what to do all the way down to the final product and then delivery and so forth. So that's kind of to frame the SME boundaries. One problem that we have with SMEs right now is technology. So if we look at your standard SME out there, there's not a lot of IT, OT staff. So if you look at the larger companies, they usually will have dedicated information technology groups and operational technology groups, and though that's sometimes even problematic in and of itself, a lot of these smaller shops don't even have sort of an IT department. They're just kind of pulling wire and hoping for the best. There's no real, a lot of the machines, people are afraid to actually hook the machines up because they're afraid that they'll get viruses, so they just keep them completely disconnected. That's called an air gap. Where you either completely isolate your operational network and don't connect it to anything, which limits the amount that you can do with it because you can't really get data off of that. You can't do any interesting analytics or use any services that are out there. And the larger ones also usually have some form of a firewall, but again, it's like the number of technology solutions you can bring to bear are very few. So that's where we start getting into some blockers. I'm going to show you, this is actually a small video on digital thread that shows you a little bit about on the design side of it, what some of the blockers are.
When it comes to manufacturing, we've come a long way since goods were made by hand. We thought we'd arrive when we could team up with machines to make things. Until we built machines that followed our orders and could work on their own. But one problem is yet to be solved. Even though today's machines are smart, they have trouble communicating with each other. They're like kids playing the game of telephone. Someone starts out a phrase that gets passed from kid to kid. But I admit, when I was a kid, I'd like to change it up a bit, just to have some fun. Even if I did behave, the message never came out the same on the other side. It's often the same with machines in manufacturing. A product's design starts out as a three-dimensional model. But if one machine doesn't have the right software, the design may have to be bumped down to a flat, two-dimensional drawing. Then, the information must be re-entered by a human so the next machine can do its job. Details can get lost in translation, and errors can creep in. A mistake may not be caught until the part is delivered and doesn't fit, or isn't what was intended. The results? Wasted money, wasted time, and stressed out workers. Here at the National Institute of Standards and Technology, we think we have a fix. The digital thread is a way for different machines in a manufacturing process to all follow the same set of digital instructions. Deviations are caught automatically, which ensures the end product is the same as the original design. I'm heading out to Middle America to see a digital thread pilot project in action. Iowa, a state that's all about corn and caucuses. Oh, and manufacturing.
Farming hasn't been the biggest thing since I was a kid. So now we've switched to high-tech manufacturing.
In the digital thread pilot, Gator's smart machines will follow the 3D instructions supplied by Rockwell Collins to make a heat shield for an aircraft circuit board. If all goes as planned, each machine in the process will understand the same digital language. During each stage of production, the product is checked against the original design and any discrepancies are auto-corrected. I'm heading 42 scenic miles south, where it all comes together. At Rockwell Collins. We're going to see if the part produced by Gator meets the Rockwell Collins specs. If you want to talk about a company where accuracy is truly a life and death matter, look no further. Apollo, Gemini, Mercury, every mission used Rockwell Collins communication equipment. Here, getting things right is pretty important. Hey Kevin, what's going on in here?
Oh, hi Tom. Hey, we're just got done inspecting the latest Gator part.
How'd it turn out?
Oh, everything came out great. It's a perfect part.
Not on any unintended holes or anything. That's great.
This is fantastic. We can take the original model, feed that right into manufacturing and building the part, right into inspection, And the same model is used throughout the process to look at the part.
The digital thread. It just might stitch together the next industrial revolution.
Has anybody heard of this? There's this concept called IT/OT and a divide between them. Okay, so IT/OT is basically the information technology and operations technology groups. And if you think about it, your IT group is sort of, they're maintaining the entire organization, the enterprise. They have their systems kind of locked down. They have the barriers and boundaries set for that. And there's only certain points of ingress and egress, and you can kind of maintain this and protect your system. The OT side, unfortunately, has taken this model here, where we've put each machine in sort of an island of automation. So the machines are separated from the rest of the environment, and there's only a very limited amount of information, only limited entries and exits that we can actually use to be able to get data in and out of these things. And it's often very, very difficult, especially on some of the legacy and older equipment. One of the problems that we also have is that machines tend to last around 30 years, which is great because you pay a lot of money for them. They're very expensive, and a lot of them are excellent machines, and they do their job fine. But from a technology standpoint, trying to get data from those machines and understand what they're doing and how to make them more efficient, the old machines don't have any ports, internet, networking, basic Ethernet wasn't even around. So a lot of them hardly have Ethernet ports. It's either serial or you end up just getting 24-volt signals. And on some of the, let's say, 15-year-old machines, we have this other problem, which is that a lot of them were shipped with early versions of things like Windows XP, and the early versions like SP0, which is just this virus magnet. You put it onto a standard network, and it becomes infected. Just the ambient viral load is enough to take it out. So you basically have to quarantine the thing. And that's where we get into this type of scenario where the OT staff basically quarantines the entire set of manufacturing equipment. The IT is out here where you have services and people and technologies and mobile apps and all the new tech that's coming out, as well as cloud-based services. So you have big data analytics and things like that are available at the IT level. But over here, because of this barrier, we really can't get any of the data out to be able to take advantage of these new technologies. So what we get into is a lot of very proprietary systems. So if we look at your standard OT-type network, you'll have each one of these applications and each one of these technologies basically having a separate connection to each one of the devices out there. And it'll cost you a lot of money, it'll cost you a lot of headache, there's a lot of time and energy put in just trying to get basic connectivity so you can drive your business applications. The solution is really around standards, and this is where I'm going to start getting into what we're promoting, what we do and why we support the MTConnect Standard. Because if you want to get efficient systems, you want to get technology that's going to make manufacturing better, be able to compete. Has anybody heard of things like Industry 4.0 over in Germany, what's going on around the world in manufacturing? There's a lot of initiatives, like in China, Germany, almost all industrialized countries right now have some form of digital manufacturing project going on. I mean, Germany's probably the most prolific right now with Industry 4.0. The US has a few of them as well with DMDII and SMLC. But for us to remain a leader in manufacturing, because believe it or not, America still is a leader in manufacturing. We're actually way up there. For us to maintain that and even gain ground, we need to be more agile. We need to be ahead of the technology curve. And that means being able to take data and apply analytics to it so we can then reduce the cost, increase quality, increase the speed. So you have the standard trade-offs here. To be able to make those trade-offs and to be able to improve our processes, we need information. And that's where things like standards come in. So the MTConnect Standard basically is a common way to get data from manufacturing equipment. So it provides a single point where you can get a vocabulary, a common set of words, a common protocol to get data from all of your manufacturing devices. It's free, it's open, all that good stuff. And a lot of the big manufacturing companies, a lot of the big machine tool builders have actually already implemented it, like Moriseki, Mazak, Akuma. A lot of these big companies have already done it. It's available for many other machine tools and controller types like Fanuc and Heidenhain and so forth. So with that technology, you can start getting data from your manufacturing equipment, and then you can start applying it to, basically bridging that IT-OT divide. So starting to get the data out of your machines. And one of the things we talk about is basically pushing this boundary. So yes, I have these machines, they're vulnerable, they have issues, but can I push this boundary as far over as possible? So now, instead of quarantining the entire system, I'm now just sort of quarantining the device itself. So this is called edge analytics or edge security. And then we can start pushing the data out with standards and other technologies and secure protocols. We can start pushing the data out. And then we can start making use of a lot of these IT technologies that are out there, like cloud services, et cetera. And then there's a whole host of new technologies and new techniques that we can use. And that's part of what this whole thing is about thinking about what new processes, what new technology will bring to manufacturing and how to be able to optimize and get maximum performance out of manufacturing systems if we have data, if we knew everything about what the machine was doing, everything about the execution, everything about the process, whether you're on process, whether you're still manufacturing to schedule, you're still making the right part, whether you have measured and created the right part, tolerances are all within spec. There's another area that we get into, things like this. So basically, as we're flowing all this information, which we're talking about, through the systems, we also have to make sure, from a security standpoint, that we trust all the data. So as we go out and we distribute manufacturing across multiple sites, and we start getting into local manufacturing. Has anybody heard about that? Some of the trends which are supposed to come out, which basically will allow manufacturing to occur locally. So instead of having to have these supply chains spread across the world, we can actually do distributed manufacturing, where I can manufacture a part anywhere in the world and basically have it come out the same way. That's one of the goals of a lot of these processes. Also, be able to have variability in the parts. So that instead of having to always manufacture the same shape or the same form, the same colors, and have a very finite set of choices, I can now have a broad choice. To be able to do that, we need to be able to trust the data that's coming out. If I'm a small shop someplace and I receive a design, I need to be able to trust who it came from. From the supplier's side, from the higher tier OEM, I need to be able to make sure that I know who it's going to and only that company has access to it. And it can only make so many of those parts. So I need to have certificates and signatures and everything. Even from the data that I collect off of the machines, I need to know that that data actually really did come from that machine. Because I could actually, one of the projects that Virginia Tech is working on is how to be able to spoof these various different documents, data, and so forth, similar to like what Stuxnet did. Stuxnet was a way to be able to spoof data coming off of machines to be able to compromise uranium enrichment. So certificates and signatures are very important. That gets down to provenance, which is basically making sure that whenever I get data or whenever I get a document from anywhere, I know where it came from and who generated it. Also, that the IP is being preserved as well. When you talk about digital rights, that is making sure that whoever gets access to it only has access to it for the purpose that they were intended. Similar to when you buy an ebook, only certain people can read that ebook. You can't just distribute it randomly. So there's also things around digital rights and digital media, which doesn't exist in manufacturing right now. So these are all areas that are going to need to be addressed from the design perspective. So I'm going to go a little bit into some basic concepts. I'm not sure. So I asked about this in the beginning. So people familiar with like lean concepts, Six Sigma? They teach it here? That's actually, yeah, interesting. Last place I was, they didn't talk about it too much. So big one is elimination of waste. Waste being any unnecessary process. So time, downtimes, maintenance, and so forth. And Mura, being able to make sure that your processes are executing smoothly. The flow is smooth throughout the entire manufacturing process. So to be able to really understand where your time is going, again, you need to get data from your system. A lot of this came out of Toyota and the Toyota production system, so talk a little bit more about how data drives it. Six Sigma, basically around quality. You have to understand how your processes are, how good your processes are at producing consistent, good parts. And Six Sigma comes from 6 standard deviations, and basically to be able to get into that 3.4 defects per million, which is the goal of Six Sigma, certain steps are necessary, and this will actually help with both of these things. The last one I'm going to go through is OEE. OEE is an equipment was actually came up by the equipment builders to be able to make sure that the equipment was functioning correctly. So it was done by the machine tool builders, and there's a paper on it which comes out of AMT, which is actually really good about how to calculate OEE and best practices. And it's around 3 different pivotal ideas: quality, a metric for quality, how many parts are good versus total; performance, how fast is my actual production process compared to what I originally predicted it was going to be; and then availability, how much time is my machine actually producing versus the time it's scheduled to be producing. And along that line, if we think about the flow, so we think about a manufacturing process. This is a value stream map coming in. So we have the supply chain, supplier coming in with the raw material that goes into inventory. Then we have our processes. We have to understand things like the cycle time, the uptime, number of shifts, the amount of time each one of these processes takes, how much time it takes in between, and so forth, and how this flows. Now, if you look at some of the automotive systems, they don't really believe in inventory. It's basically single part flow all the way through. So it's just one part being passed station to station, flowing through the processes. And then how we schedule these processes. This is the way we do it right now with weekly and daily schedules for each one of the different machines. But again, as we start getting into some newer systems and we start getting a better handle on our data and what our machines are doing, we'll be able to get to systems where we can do this in near real time. We can start scheduling based on the performance of each one of these systems and do rapid changeover. These value stream maps are fairly static. We need to get to a more dynamic version of value streams. To be able to do that, we need to understand time. And I'm going to go a little bit through OEE now. And we understand, so this is basically understanding where time goes. And one of the important things you get from understanding how your machines are operating, if you can collect data from your machines, you can actually start to understand how each one of these buckets are being executed actually on the machine. So you can start, you have your plant schedules, you have your scheduled downtimes for the machines. Delay time, this is when you're waiting for parts or some process, upstream process. Repair time is your maintenance time, so that's unexpected. And then we get into our non-process times. Non-process times are times when you are doing things like setup, tear down, part changeover, to the point where we get into actually our process time. Our process time is a time we're trying to, this is our good time. This is the time we're actually making chips, executing a part program, doing value-added work. The idea is to try to reduce this time down as much as possible. So if we look at from our scheduled downtime, this is, according to our schedule, this time here, these buckets from delay, repair, non-process, we're trying to reduce those as much as possible so we can maximize this and have the machine operational as much as possible. And if you're not collecting data, it is really hard to be able to optimize that time. So, this is a quote from Calvin. Basically, if you don't measure, you can't improve. And again, to go back to that number, only about 5% of shops right now are collecting data. And if you're not collecting the data, if you're not understanding what's really happening on your shop floor, it's almost impossible to really improve those systems effectively, because you have to understand what the machines are doing, and you need to do it in near real time so you can react to problems that are occurring in the manufacturing and execution systems as they're happening. And this goes back to the small to medium manufacturers. But what are they worried about? Quality, on-time delivery, making sure their processes are consistent, executing correctly. They need operational visibility. And this is actually operational visibility goes up and down the supply chain. So if you think about it, a small to medium manufacturer, if they could report up how effectively they're executing upward, it may actually help them to increase the visibility of their processes and reduce the number of surprises if things are running behind or if they run into a manufacturing problem. They may be able to get the higher level whoever they're supplying to understand what's going on and make adjustments more proactively instead of waiting until it's too late. So actually information and visibility, this has happened actually in software too, where visibility actually helps to increase the effectiveness and the satisfaction of the people that you're supplying to. And the last one is basically, this is based on theory of constraints, which comes out of Goldratt. And the operative goal of almost every company is to make more money now and in the future. It's kind of an obvious one, but people often forget that. The goal is to just keep improving and keep improving and keep growing. So now, what is MTConnect? Let's talk a little bit about it. So MTConnect itself is a way to get data from machines in a common format. So basically, we think about what machine tools are giving us as far as data. They're giving us a whole bunch of different things. This actually is sort of a pretty printed version of the standard, but you can understand things like whether it's an e-stop state, you can understand what block of code it's running, whether it's in automatic or manual mode, what line of code it's currently running, programs, feeds, speeds, positions. It gives you that raw data coming off the machine. It tells you exactly what it's doing at any point in time. And the big thing is that whether it's a new machine, an old machine, or different vendors, different builders, different controllers, the data is always the same, meaning that an X position is always going to be in millimeters, and it's always going to be called a linear X-axis, and it's always going to be in millimeters, and it's always going to be called a position, and we're going to know what the coordinate system is as well. So that consistency allows you, from an analytical perspective, to be able to take data from multiple different sources, multiple different types of equipment, and apply the same analytics to it and achieve results without having to reinterpret that data from every single source that you're going out to. And it's read-only because we didn't want to have any safety issues stopping us from deploying. So one of the big issues you have in manufacturing, and this is actually industrial internet if you think about it, the big difference between industrial and consumer in cyber-physical, if you want to also use that term, cyber-physical systems, is that cyber-physical systems have a safety issue. Whereas if you're merely just collecting data from, let's say, a sprinkler system or a health monitoring system, there's very little chance that that system is going to actually cause any damage or hurt anybody or have a safety issue. Industrial systems have safety issues. Basically, a machine tool, if for some reason it happens to start up when you're not expecting it, can kill somebody. It can rip an arm off. They're dangerous pieces of equipment. And because of that, we didn't want to get into the situation where somebody was going to be compromised, where safety of the machine is going to be compromised, so we made it read-only, meaning that you can't change the operational states of the machine. So it's a data pipe coming out. We used, at the time, the prevalent standards, HTTP and XML. In the next versions, we're going to be going over to things like JSON and MQTT, things along that line. But the deal is, with MTConnect, you can use any standard technologies and handle the data. So it's very easy from an application standpoint to be able to collect data from machines, process the data, and understand the semantic meaning of the data. And that's where the simplicity comes in. So are people familiar with various different manufacturing processes? MTConnect first focused on primarily milling and turning processes. We've recently got into things like wire EDM. There is a group that's now thinking about additive, and some of the machine tools now, some of the milling machines are now doing this hybrid additive. Heard about that? Where it's a little bit of both. Are people familiar here with wire EDM? Okay, great. Yeah, a couple. Yeah, sometimes people don't know too much about that, but it's something that we're getting into right now. And we also handle both CNCs and PLCs. So for milling and turning processes, we've integrated with most of the big controller and machine tool builders in this space. And we've also added, in a couple of cases, sensors. So the other thing that MTConnect provides sensor data, semantics, across a broad array of sensors. So we went into sensors, we found that there wasn't a good standard out there for collecting data from like even thermistors, vibration, acoustics. It actually surprised me when I found out that there were no standards out there which standardized the units and the vocabulary when talking about these things. So MTConnect actually took that on as one of its tasks to standardize sensor data. So one of the things you can do is actually hook up like an Arduino or a small sensor device and get data and pipe it through MTConnect. We've actually done it at up to like 8 kilohertz in XML, which is even more bizarre, but it works. And it's pretty effective. I can even show a demo at the end of this if everybody's interested. We handle motion, various different axes, rotary and linear motion. And we handle the translation from PLCs and CNCs to the common vocabulary. So when we talk about things like machine tool states and so forth, we handle all that. For wire EDM, one person heard of it, we're now working on standardizing the vocabulary around wire EDM processes. These are machines that take incredibly highly charged wires and cut through hard metals like titanium. And they're great for doing roughing operations where you want to be able to remove a lot of material. If you think about it like taking a hot wire and cutting through styrofoam, that's pretty much what wire EDM is, but for metal. And there's a couple of different flavors of this. There's your wire where you're just dragging the wire through the piece of material. Some really complex geometries because you can actually twist the wire in various different ways. We're also working on sinker EDM and other EDM processes where you have an electrode even up to, I've heard, the size of a car bumper, which can basically plunge and remove huge amounts of material very quickly. We're going to be modeling high energy power sources and dielectrics, pumps and tanks and so forth. So all those types of systems and components are going to be modeled within MTConnect. So to look at sort of a high level of where MTConnect comes in, people familiar with any of these other standards? ISO 13399, QIF? Yeah, so ISO 13399 is a standard for cutting tool geometries. It's basically a document that will describe all the bits and pieces of a tool that you need to be able to assemble. ISA 95 is a process standard that tells you about all these processes to be able to make something. And QIF is a standard for quality information framework, comes out of Dimensional Metrology Standards Consortium. These are all documents, and they're domain models. Basically, they're information models that describe the vocabulary, the semantics around a particular type of concern. At the other end of the spectrum, you have things like OPC, Profinet, and Ethernet IP. These are standards that provide communication protocols and a little bit higher than your standard like Ethernet, which is just basically blobs of data. They provide syntax around it. They tell you like key value pairs and so forth. And that's where these guys fall in. MTConnect is kind of in the middle. We provide the semantics, the domain model, the vocabulary around each one of these different areas, as well as we also provide the transport. We just use HTTP. We actually can layer on top of these other standards, like we have an OPC UA companion specification where you can send MTConnect data through OPC if you want to, and use OPC UA if you want to use that as a transport. But then you're still using the MTConnect data model. We really focus on the data model. So if we had to give up one thing, we'd give up the communications layer and just focus on vocabulary. Because when you come down to it, the vocabulary is what really drives analytics. Being able to use that common terminology for every single piece of data you're getting off the machines gives you a huge boost when you're trying to figure out what does this data mean and then become predictive, proactive, and develop your applications. So the architecture of MTConnect is basically this. You have, go through it quickly, call native adapters. So on some machine tools, especially some of the newer machine tools, you'll have an adapter which sits right on the machine tool itself. So like on a Mazak or in Siemens controllers, the adapter will basically be embedded within the controller, and you'll run it on the controller itself. You can add additional sensors to that machine. Let's say you want to get coolant temperature, or you want to get vibration or acoustic signature off of one of the components. You can add additional sensors on that. The next is where you have an older machine tool, let's say a 20-year-old machine, and we can do what's called a legacy adapter. A legacy adapter is basically a small software component which then usually hooks up to things like the 24-volt wires off the PLC and interprets various different binary signals on the machine to translate them into MTConnect vocabulary. The third is networked adapter. And the network adapter translates from whatever the proprietary network-based protocol like Focus2, LSV2, there's a whole bunch of them out there, to the MTConnect vocabulary. Now that just is a first step. We're getting the data off the machine. The second is the agent. The agent provides the HTTP protocol and translates that data then into XML. So we have basically these translators from the machine's proprietary APIs or the machine's proprietary protocols into the MTConnect standard. And from an application standpoint, all I need to worry about is this one agent here. And the agent itself just speaks HTTP. It looks like any other web server to the rest of the network. So when you're interacting with MTConnect, you're just basically making HTTP calls and then getting data back, either streaming or otherwise. And it gets back into your application, and then you can run your analytics in your application. And again, it's read-only data flowing out of devices. You have your various different inputs. They all go to the agent. Now, one interesting idea about this is that we talk about sensor fusion here. And we're getting this binary data off of the machines, off of our sensors, and we're fusing it together. And what we mean by that is basically MTConnect has this idea of timestamps, which is something everybody knows about and seems pretty obvious. But if you don't timestamp every single piece of data, you can't really reconstruct causality. So one thing that we do is we allow different data streams to be merged together and given a consistent timestamp. We do that in the agent. The agent can even do what's called relative time, where it can correct for clock drift. It can also have a millisecond offset and be able to then reconstruct the real time off of that. So every piece of data that you get has an existing timestamp associated with it that allows you to then figure out, when the machine was in this certain mode, this was the sensor data that I was collecting from it. So this was a temperature, this was a vibration, these were the loads on these different spindles, this was the position they were in, this was the spindle speed, feed rates, all the different data about that machine. Now I have sensor data coming out, and I know exactly when everything happened. And the timestamps also allow me to be able to collect data, and if I don't collect it every single millisecond, I can still reconstruct that entire chain of events and associate them together. So the first step is we get this data coming out. It's all fused together. And then we first step is sort of a syntactic transformation. I talked about things like OPC, Ethernet IP, and control in various different protocols. That's where you're basically assigning a tag value. So the tag is some arbitrary name you give the data, and then the value is some value in some set of units that are probably local to the machine. And to be able to go to the next level, this gets you a certain step. And if you stop here, the problem is that even if you know what type of data is, I know this is an integer, I know this is a floating point number, and this is a floating point number, I know this is an integer, I still don't know exactly what that data means. Right now, these are basically uninterpreted. A lot of the protocols that are out there right now stop at this point, at the syntax layer, like OPC stops and Ethernet IP stop at the syntax layer. You need to go to the next level, which is basically the semantics, where you have a model of how the information is associated with each other, basically the components of the machine, the linear axes, the rotary axes, and then the various different pieces of data that are associated with that, be it the angle, the rotary velocity, the positions, and then convert them into a common set of units. So here we have 5,196.54 millimeters. The load is 12.43. That's actually a percentage. We know this is now an RPM, and we know that 2 happens to be translated into an active state on the controller. So we need to translate it into this common vocabulary and then do interesting things with it. Once you do that, then you can start writing your applications, and you can start actually getting knowledge and information from the system. This is just raw data, pretty much. That's the whole value proposition. And as we start to bring data from various different systems together, and as we start to integrate it, the idea is that we're going to bring multiple different services. So if we look at, let's say, equipment manufacturers, this is the area that we're providing. MTConnect is really a service. If you think about it as an HTTP RESTful service where you make a request, you get data back, and you know what the data means. That's what this guy is here. Eventually, design systems and supervisory systems and engineering systems at different levels will also be providing services that we can then integrate these things together. And this is the first step of being able to get interoperability between multiple different systems. That's how we're going to be able to make, if you talk about, next industrial revolution, by interoperability and integration of data and services from the entire digital thread, that's how you get to that point. And that's how we can start to achieve some of these things like self-optimized and self-aware systems.
Okay, we're back with the gang to talk about the student challenge again, and I know, that Will and Helena have been to, you guys have done what, 6 workshops, live workshops across the country?
7.
Yeah.
7 live workshops across the country. So, and Tim, I don't know if you got to any of those, but I know that because you're the, you got that VP of Manufacturing Technology in your title. I love that. It makes you really, really one of the smart guys. I have to believe that there were a lot of questions from the students. I mean, I'm going to, we want to answer questions that people are submitting to us online as well. But I have to believe that there were a lot of questions. Will, I want to start with you. What were some of the questions, most common questions or best questions that were asked while you were out there?
So in visiting colleges, a lot of the students asked us if they could use an existing project that they're working on, either their master's or their PhD thesis, as part of the challenge, or whether they had to create a new body of work. And that was one of the, they were concerned. So what's the answer to that?
Yeah, Helena, what is the answer to that? I'll let you do the.
No, we are not expecting students to create completely new projects. If their current project uses data in any shape or form, then it would qualify for the student challenge. It would qualify the submission for the student challenge. Do note, though, the data should be MTConnect.
Okay. And I'm just curious, though, Valerie, and I'm sorry, what was the other, the second place winner's name?
Joel Neidig.
Joel. Okay, Valerie and Joel. Did they use projects, were those projects they were already working on, or did they start new?
In the case of Valerie, she actually heard about the challenge as she was looking for a topic for her thesis,
oh, okay.
for her master's thesis. and she formulated her thesis around the student challenge.
Makes sense?
Enough, she submitted for both ideation and application. She didn't win during the ideation round, but she won during the application round.
Good for her. Good for her. What other questions, came out during the sessions? Will?
The other big one was, if I have one idea, can I submit it for both ideation and for application? Or do I have to have two separate ideas for each part?
Okay. I'm going to put Tim on the spot for this one, all right?
Gotcha. Well, since both formats actually are different, a single idea could be an ideation as followed on to be realized in an application, or you could have two separate ones. The point is that they're both eligible. And so any idea that takes MTConnect and thinks about a business case is just as eligible for the ideation phase. And if you go further with that and you put some MTConnect Standard compliancy to an application, you're just as well into the application, but they don't have to be either ors or first step, second step with the same idea. It can be either case.
Okay, that's great. Helena, what about you? You've been there. What are the other frequently asked questions that have been popped up at you?
One of the frequently asked questions is, do I have to submit as an individual? Can my submission be a group? And does that group have to be within my school, or could it be, can my teammates be from other schools? The answer to that is, first of all, you can submit as many ideas and as many applications as you can, and there's no limit to the number of people that can be on a submission. There's also no limit regarding affiliation, so you can team with anybody and everybody as long as everyone on the team is enrolled at a U.S. community college or university.
Okay. Okay, so Elena, what other questions did you have while you were out at the sessions with Will?
One of the questions is around eligibility. Does one have to be a U.S. citizen in order to enter? And the answer is no. All students who are lawfully admitted and enrolled in a degree program at an institution of higher education are eligible to participate.
And that's the pure definition. You just kind of threw me. Lawfully admitted. How do you become unlawfully admitted into a? I don't know how that works anyway. So, were there any other questions that people were asking about?
Yeah, Steve, I had a question that came around the, we got some great prize money, and obviously it takes some resources to pull a challenge off. So, Helena, where is the money coming from?
The money is coming from the Office of Secretary of Defense, Defense-wide Manufacturing Science and Technology Program. And the project, I know you didn't ask this, but the project is being executed by AMT, the Association for Manufacturing Technology, MTConnect Institute, U.S. Army Benet Labs, NCDMM, that stands for the National Center for Defense Manufacturing and Machining, and in partnership with SME and NTMA, and that stands for National Tooling and Machining Association.
A lot of people involved. Hey, thanks for the shouts out.
But SME, we also know it can mean a lot of different things. So, Society of Manufacturing, just to make sure. So anyway, and I don't want to drop it by by cutting you guys off right now. Are there any other questions that you think people would want to know the answers to right now? I'm hearing cricket, so I would say the answer to that is no. So, but I want to jump back here real quick and just show the deadlines for application. Make sure that you get your submissions in time. Don't want to miss that. And if you do have any other questions, please feel free to contact Helena at the Association for Manufacturing Technology. I can't believe I couldn't say that. And You know, if you don't remember the number or anything like that, you can just go to AMT online and contact them through there. So Will and Helena and Tim, thank you very much for answering these questions for us. And I know that I'll be seeing you in future programs. Thank you very much, you all.
Thanks, Steve.
Thank you.
Thanks, Steve.